Hi everyone, welcome to the NOAA Central Library and the NOAA Innovators Series. We're very excited for today's talk. Quick note, I am librarian Katie Rowley. We're in the Silver Spring office right now. For the webinar, if you do have any questions, there is a question panel. Everyone online is muted, so if you do have a question, please place that in the question panel and we will answer those at the end of the webinar. I'm going to turn it over now to Derek Parks, who is going to introduce today's talk.
Thank you very much, Katie. I'm joining everybody here from the snow-dusted Rockies in Boulder, Colorado. It is an absolutely gorgeous view here, and I know you all are jealous that you don't have snow wherever you are. I don't know. It's almost June, so probably not that jealous. But so I'm happy to present our two speakers today. We have a really great Innovators Brown Bag this time, basically going over a brand new success story that we've had, a technology transfer success story. So I'm looking forward to hearing a little bit more from these two gentlemen, but what I will do is give you a little bit of a background on the technology first and then introduce our speakers. So today we're going to be talking about a new and innovative water level sensor that was developed by the Alaska Pacific River Forecast Center. And they built this to fill in data gaps in Alaska's current water level sensing network. And they ended up deploying about 40, the gauges to about 40 different locations in and around Alaska. But as you all know, it gets a little bit cumbersome to build your own devices in the lab after you've come up with the technology. So what we did is we entered into a cooperative research and development agreement with Stillwater Technologies to actually develop these commercially, and that way we can have a nice development process and a good commercial success story, but also a good source of these gauges for Alaska and also for anywhere else in the NOAA network. So that is what we're going to be hearing about today. And our two speakers, we have David Schoenmaker, who is the software and hardware engineer from Stillwater Technologies. And so David grew up in the Seattle area, spent his entire career in software and hardware development. And in addition to working software development for Microsoft, he has experience in wireless, cellular, and data communications as well. And outside of work, he enjoys flying, amateur radio, and continuing to learn. So that's a little bit more about David. And then we also have Crane Johnson, who is a hydrologist from the Alaska Pacific River Forecast Center and our inventor for the iGage device. And Crane has been living and working in Alaska since 1995. He's a registered civil engineer, and he spent most of his career working on water resource projects, including over a decade of water control and flood forecasting experience. And outside of his work, Crane enjoys skiing and hiking in Alaska's mountains, so I'm sure Crane will appreciate my snow-covered mountain vignette from earlier. So with that, I will turn it over to Crane to get things going.
Yeah, thanks, Derek. Thanks for that introduction, and thanks to the library for hosting the Brown Bag today. It'll be David and I both presenting this presentation, and we'll cover generally sort of why we came up with the idea for these low-cost river stage sensors, cover a bit of the technology, the development timeline, and then we'll talk about the CRADA and the new products that are now available as off-the-shelf products from Stillwater. That there is a picture of Lowell Creek down near Seward, Alaska. Just a bit more about my background, as Derek mentioned. I'm not don't have a academic training in electronics. I've been a civil engineer in Alaska for about 15 years. But early in my career, I worked for a hydrology research group and did a lot of field river monitoring, and worked in and around electronics quite a bit, and was interested in the sort of the smallest possible sensing we could do on rivers. That combined with, recently in Alaska, we use these satellite tracking devices, and to see those handheld was sort of some of the inspiration to try to miniaturize the a river stage gauge. And so that, along with some computer programming skills, was where I came from in terms of background.
Yeah, and I'm thank you for having me here today. I appreciate the opportunity to to participate. Like Derek had said, I'm a Washington native, which is kind of rare these days, and I've worked mostly software and hardware development with Seattle companies throughout my career. Stillwater Technologies has actually been in existence for about 25 years, doing various contract and consulting contracts. And after leaving Microsoft, then it's kind of my post-corporate endeavor. Reduced my commute by about 90 to 90 minutes a day, and so then I came across a NOAA technology sharing site one day, and the iGage sounded very interesting to me because of both the hardware and the software aspects. So that's where it all began, and Crane and I have been working, pretty closely since then.
Yeah, thanks, David. I'll go in a bit background on sort of how we came across this idea. I work for the River Forecast Center, and there on the bottom of your screen is our basic mission. It's to protect life and property and enhancement of the national economy. But generally, we monitor rivers across the country for a few different reasons. Flood monitoring is the obvious one, but fisheries, navigation, water quality, recreation are other uses. Across the country, this would be a sort of schematic of a traditional river water level station that the USGS runs. They're the primary collector of river discharge and water level information across the country. And generally, they're fairly expensive to install, but they are necessary. In addition to the water level monitoring, the USGS maintains a rating curve, which allows us to go from river water level to river discharge. And so while expensive, these stations are still important, and we always want to sort of highlight and emphasize the need for these traditional water level stations that also monitor river discharge. But in Alaska, we definitely have a sort of an area issue. The image on the top left is state of Alaska, the outline of the state of Alaska with the water level stations that are currently in operation as the dots. And to the right is the Northeast U.S., same scale with the water level stations, again, as dots. And so it just gives you a visual of the lack of data we have in Alaska to understand both our streams, our smaller streams and larger rivers. And so in Alaska, we basically have one USGS stream gauge for about every 6,000 square miles. And if we were to look at the state of Connecticut, which is smaller than 6,000 square miles, there's currently around 77 USGS gauges. So we're always interested in trying to augment the traditional USGS gauges with other technologies. So what we like to do is sort of augment these either upstream or downstream or nearby sites with just a simple river stage measurement. And our initial requirements were something low cost, small, easy to deploy. We wanted them somehow protected from flooding, scalable, solar powered, and it would work through our Alaska field season. At a minimum, the open water season, which is from April through maybe mid-November in most cases. Some of the initial concept drivers were back in the late 2000s, early like 2008, 2010. I think I came across a project in Iowa where they had done something similar, a little bit larger scale, and it used cellular technology, which for us in Alaska, it really doesn't work well. And in a lot of cases, rivers are always at the bottom of the valley, so just naturally they'd be challenged for cell coverage even in areas with good cell coverage. So around the same time, Iridium and other sort of low Earth orbiting constellations were becoming sort of more available in Alaska, and so that was sort of one idea was this the form factor and the power requirements for satellite telemetry were shrinking. And then sort of right around the same time frame, there were a few manufacturers, I think thanks to robotics and automotive technologies, that had really dropped their price point for acoustic distance sensors, probably on the order of a magnitude in sensor price point drop. And so the idea was to sort of combine those. It's a couple of example applications where we wanted to use sort of combine, all-in-one package with a satellite with a distance sensor would be sort of small streams in the top left. That's Jordan Creek down near Juneau, Alaska, or larger rivers in the center. That's the Susitna River in central Alaska along the Denali Highway, or even just to measure snow depth. The idea was this sort of small package distance measuring equipment that could measure not only water but anything else you could get an acoustic return off of. And then we always had in our head, back of our head was to somehow monitor a rain gauge as well for hydrology. That's sort of, we're always interested in both what falls on the ground and then what runs off in our rivers. So it was around 2012. I came up with an sort of initial prototype, and it was pulling together the sensing technology with the satellite technology with a custom developed CPU board, and the black diagram just shows basically how the devices work. It's got a small CPU that controls everything. There's the digital temperature sensor, an acoustic distance sensor. There's onboard memory and a real-time clock, and then all the data gets put in a small packet and transmitted via the Iridium satellite network. The picture on the right, that's the very first unit we fielded. It didn't have any solar charging and just ran off 6 AA batteries, and would go for about a month on the 6 AA batteries. Real quick, the theory of operations, it's pretty simple. And this covers a lot of our initial requirements. They're flood proof. They're put on bridges. Bridges are generally designed to be above the 500-year flood. They're small. They're easy to install. And the sonic transducer is just pointed downwards, and it's a simple ultrasonic distance measurement. We then reference the gauge to a known elevation on the bridge, and we just get the river stage equals that known elevation minus the distance the device measures. And typically for our application, we transmit the data once per hour. As Derek mentioned, so the initial prototype was 2012. In our lab, we tinkered away and made some improvements over time. And then by 2014, we had a design we were ready to sort of push out to our field. And so we started with quantities of 5 to 10 units. And between those first 2 years, had sort of built and installed around 40 units, and had started to share it through a few internal NOAA meetings with partners, and within Alaska with hydrologists within Alaska. And there's definitely been interest, and we've worked with state partners within Alaska to help furnish and install iGages. But we quickly realized that we weren't capable, nor did we really want to. We want to stick with our main mission, and that's forecasting for rivers. But we felt that we quickly realized there was a need for iGages from both interested internal users and external users, and even within our group, we were starting to see that it'd just be easier and more efficient to have a commercial source to actually just purchase one of these off the shelf rather than build them in our shop. A quick look at the timeline. So 2010 was the initial concept, right around there. 2012 first prototype. Alpha design on what we wanted in the field was early 2014, and then I think we had 20 units that first summer. One of the conferences we presented at was the NOAA Emerging Technologies, and that's when we were linked up with Derek's office and came up with the idea of a CRADA, which was sort of the perfect vehicle to maybe get these into commercial off-the-shelf technology. That was advertised in early 2017. And then in the summer of 2017, we connected with Stillwater Technologies and David, and we basically started working together collaboratively to transfer the technology and make these available both for ourselves and for other users that are interested. And I think that's worked very well. And by just last year, these are basically available, and our office has begun to, rather than build them in-house, just purchase them from Stillwater, which has worked out well for us. I think a couple of the sort of keys or steps to success, it was David and I haven't met in person. It's all been through email and telephone, and that's worked out well. That was early in the beginning. It was early and often, just sort of sharing sort of what we've developed and answered any question. We kept, I think, decent documentation. We're not a sort of R&D, and it's definitely sort of outside of our normal what we do day to day, and so we don't have all the procedures in place for sort of product development, but tried to keep decent records that we shared. One thing we did take advantage of was NOAA's B-Lab service, and that was a sort of common place where internally I could get to, and externally we were able to open it up to David's company and share hardware and software source code, so that we had a version tracked repository where as David made updates, we were able to sort of see those and collaborate on the updates and discuss them, and it keeps it in a sort of centralized location. And then as the Stillwaters develop these, we continue to provide feedback, as we have purchased these iGages and see maybe different areas of improvements. I just make sure I feed those back to David. And I'll hand it off to David. He can tell you a little bit about Stillwater and the product he's put together.
Like I said before, Stillwater is a privately owned small business. I'm a veteran. We're based in Carnation, which is just east of Microsoft in Redmond. And I've worked in hardware and software my entire career. I kind of started off in the hardware business when my dad, a long time ago, actually worked with sonar on submarines. So when I hit the schools, I discovered that there was also software, and I kind of got into the software track, but have worked in both areas my entire career. The CRADA and working with NOAA seemed like a perfect opportunity. I like the technology, and I like the opportunity to be able to actually manufacture something. As a software engineer, a lot of your career, you're working on things that may or may not ever really appear in a product, and oftentimes it may appear but then disappears. So I've always been intrigued by manufacturing something that actually stays around and you can see a physical representation of your work. So for me, this has been fun and a great opportunity to learn more about river monitoring and water levels. Some of the key things, cranes covered a lot of this, but basically the acoustic sensor will measure up to 32 feet. On a good day, it'll actually do quite a bit more than that, but you really can't guarantee that. The sensor we use has a noise filtering algorithm that makes it filter out noise, gives it a little better resolution as well as repeatability. The iGage, what is really nice is it's a small 5x7x3 container that it's totally self-contained. So you can take this and nail it on a branch of a tree and be receiving data within minutes. Absolutely no infrastructure required. It does require some sun because the battery solar panel charged. But again, with the Iridium network, you can put one of these anywhere around the world. And right now we have iGages from Southern California through the Central Valley up to north to Alaska. So I guess as far as my northernmost installation is in Kotzebue. One of the other things we've been working on is we're using a digital temperature sensor because one of the things we've noticed is the temperature change during the day affects the readings slightly, and if we can get a true temperature, air temperature, our accuracy will increase. As you all well know, temperature varies from temperature can vary, depending on the sun as well as wind and shadows, and so we see that variation, and we continue to try to work on getting better and better temperature measurements. We've also have done some improvements to the circuit board layout, and our right now we've got a new circuit board in the works that will be slightly smaller and more easily manufactured. We've also developed the rain gauge interface that allows you to connect a tipping bucket type rain gauge to record rain accumulation, as well as adding a radar sensor, which greatly improves the distance capability, as well as meeting some of the USGS requirements for water level accuracy. One of our customers required an alert because his iGage is deployed along a highway, and when it reaches a certain level, it floods the highway. So we've added an alert threshold that allows you setting a level, and then once it reaches that level, it increases the reporting frequency. For instance, typically we report once an hour, but once it reaches that alert level, you can program it to start reporting at a increased frequency. So that is working well for him. And the other nice thing is that everything is programmable after installation, so you can reconfigure the iGage through the Iridium network. As far as the radar gauge, we basically integrate a waterlog type radar. Waterlog's the manufacturer, and they have 3 versions of it that measure from 0 to 20 meters, 0 to 40, and 0 to 7. Surprisingly, is the radar, of course, is quite a bit bigger, but it's very, very low power, not much more than the acoustic sensor. It's less than 15 milliamps, but it runs on 12 volts, so that added some engineering challenges to make it work with basically the iGage board and power sensor. We've got a couple of these deployed. One's in Kotzebue. It continuously reported throughout the winter. It's been there just about a year now. Slightly larger form factor. It's in like 11 by 17 box, 7 inches deep. the radar itself uses an SDI interface, which basically we just added to the iGage board.
Yeah, thanks, David. This is Crane again. I can talk about a few of these slides, and just this is one example initial installation that we had in Alaska, and it's out on the west coast, and it basically just shows a sort of typical bridge mount installation, and then how we display within the Weather Service. We display the information on what we call a hydrograph, which just shows the water level on the left axis over time on the x-axis, and it just shows sort of the information we get when we take the distance measurements and calculate river stage. This was on a coastal lagoon, and it was tidally affected, so that's why you see the up and downs regularly. Another installation, and what we've done is in a few places have co-located these next to sort of the higher quality, higher accuracy USGS gauges. And you do see differences. The typical accuracy is on the order of 1% of the measured distance, and it's mainly due to that variation in the speed of sound due to temperature. And one of the challenges will always be with acoustic sensors is that while you can measure the air temperature accurately at your sensor, the temperature of the air column can change, and it likely does as you get down to the water surface. And so that's always going to be an unknown, and we see that in the signal. You'll see small diurnal changes in the distance measurement that are likely affected by the air temperature. The graph on the left is just another example of a sort of iGage in the field and the information we get. The 1% distance, for our needs, for flood forecasting, for sort of general understanding of the rivers, works pretty well. There's definitely limitations for really small systems, systems where you're interested in scientific study. You'd probably lean towards a radar type sensor, or one of the in situ type sensors that can give you the higher accuracy. Typically USGS, other agencies are looking for accuracy on the order of 1/100th of an inch or of a foot, absolute accuracy of the sensors, and the iGages don't do that, but they provide you on the order of a tenth of a foot to a tenth to on the order of 1 to 2 inches of accuracy, depending on the distance measured. The slide on the graph on the right just shows the co-located iGage with the USGS gauge, and so you do see sort of residuals between what the USGS measured and what the iGage recorded over time. Other applications we've thought about are snow depth applications, and this just gives a couple examples of the super simple mounts. I think initially when I came up with the idea, it was maybe in addition to river water level monitoring, these would be sort of rapid deploy gauges that, if there was flooding, just like David mentioned, maybe a highway gets overtopped, and while you may not have it in place at the time, if you had, if we had an inventory of these, we could always field them quickly to monitor, say, problem locations or an area where, all of a sudden we needed, hourly or 15-minute water level measurements over time. And these could just be, quickly deployed either on street signs or minimal hardware required to get them out.
So in addition to manufacturing and selling the iGage, we, as part of our service, provide an extended technical support and warranty on an annual basis for an iGage. And for this, you get any of the configuration or technical support you need via email or voice. It also covers any failures not caused by the damage, abuse, and vandalism. And if there's a problem with an iGage, we'll repair it for free under the contract. And then also as part of this, we set it up so that for customers that don't have their own data repository, we set it up so that it reports directly to our servers, and we provide the airtime subscription as well as data storage for customers. So essentially, like some of my customers, they don't want to really mess with the data. They just want to be able to see the water levels. So they've got a website they can go to and look at it. It has, again, as I'd mentioned, alert levels so that if it exceeds a certain level, it will text or email an alert to you. They can go online, actually look at the web pages, see the recent reporting levels as well as a graph. And we also have web services to actually query the data and export it so that you can actually use it on your own website or transfer to your own databases. We retain storage for at least a year. Again, these data packets are pretty small, so typically I won't run out of data storage for a long time. Currently, it's hosted on our own web servers, but one of our projects is to move it to an online system. Cloud storage is what I was trying to say. And also, we're developing a web configuration page that allow you to configure the iGage through a web page, so that you can modify the configuration as you need. Typically, the configuration is mostly concerned with reporting levels, so, and frequencies. So. Here's some examples of our basic web pages. You can see on the left, there's a master page per group, and it shows the iGages you have installed. And then if you go into the detail of it, you can see the reporting for the last 48 hours, and that's of course adjustable. And on the right is the typical graphs for a website. So, so this was developed. We've done various things to try to maybe make it a little more flexible and actually generate a little larger market than just river gauge storage. And one of the things we've done is been able to add a GPS to it. So then again, like Crane was talking about for rapid deploy or emergency type deployments, you can take a iGage out, and with the GPS, you can report the location with the reading. So you could actually put it on a mobile type situation that you could go out and measure different places. Again, road and highway monitoring, there's lots of interest with that, as well as with even the snow levels on passes and stuff. It gives the DOT a good indication of what kind of snow came down in the more remote locations. Alaska Water Level Up is using it for coastal monitoring, and one of my associates has a little place on a river summer vacation that he says he's would like to deploy one there to watch the water level on the river, so that in fact he can get a warning when it starts approaching flood levels, that he can go up and rescue any of the floatable objects in his yard. And we've been talking about a possible use for groundwater monitoring. And then some of the things we've been playing with and thinking about is, we could do an Alexa skill. So you could query your Alexa for specific water levels. And that's kind of a fun idea. I don't know how much it would be applicable, but you know, that's kind of is trending and be kind of a fun thing to do. And as well as having a phone app that actually pushes the notifications. So you could actually see water levels, you know, on your phone in real time. So just about everybody I talk to has some idea of what it could be used for and how they might use it. So I think it's got a great potential. It's really been fun to explore those ideas and expand on them. One of the other enhancements we did too was we built a little larger one, which is a 7x7, and puts double the battery capacity into it, so that it'll reach further into the winter seasons without good sunlight. We've got one of those deployed, and anxiously watching it to see how it performs. It uses a little bigger solar panel, and like I said, double the capacity, but otherwise it's identical to the iGage. The one we have deployed has a tipping bucket rain gauge on it as well. So that pretty well is where we're at. So.
Yeah, thanks, David. This is Crane again for everybody, and just want to thank Derek. I mean, without the connection through the technology office, David and I would never have met, and it's been sort of win-win for our office at least to sort of get the technology over into the private sector and be able to just purchase these back for deployments.
Yeah, thanks, Crane. This is Derek again, and thank you both for an excellent presentation. I wanted to, if this is an appropriate time, but let me know if you've got a little bit more to talk about. But I wanted to go into, just give people, since I don't know who's on the line, give them a quick background on the CRADA and how you can use that. Is that okay with you guys?
That sounds great, Derek. We're all wrapped up, and we can go through that and then take questions later.
Excellent. So I'm in the Technology Partnerships office in NOAA, and we serve all the NOAA line offices with two different programs, the Technology Transfer Program, which is the one that I manage, and then the Small Business Innovation Research Program, which Vince Garcia, who's also on the line, manages for us. But in this particular case, we used a Cooperative Research and Development Agreement, which is a template agreement that just allows NOAA PIs, NOAA labs to engage with the private sector, generally for this particular purpose. The idea is to do collaborative R&D towards a product that will go and then be used by the private sector collaborator, be sold by the private sector collaborator. And the general idea is that through combining the resources of the federal government and the innovation of our researchers with the innovation of the private sector researchers, we come out with a better product in the end. And everybody benefits, truthfully, from that engagement. So using the CRADA is a little bit different. Sometimes I think a lot of people believe that you have to go through a patent route or some other type of protection to get a technology out to the private sector, and that is not always the case. Sometimes that makes more sense for the company. They want to have that de-risk as much as possible any additional investment that they're making. But in some cases, yeah, we just want to do it as quickly as possible. And in this case, the CRADA was a pretty rapid implementation. Guys, I don't remember, I don't have the data in front of me, but it took us, a couple months to put this together and get things rolling? I don't recall exactly, but it was quick.
Sounds about right.
Which is, yeah, it's not something that you normally think about with the federal government, being able to rapidly get something out to the private sector and start enabling sales. So we're really, really excited about that. Do you guys have any thoughts in particular about using the CRADA that you wanted to share with people? Is it something that you would recommend, or did you have any issues or anything that you wanted to let people know about?
David, I'll let you go first, and then I can follow up.
Okay. I thought it was a great mechanism to get going, and I thought it was first of all, stumbling across to this. I was checking weather on the NOAA site. I thought, hey, this is pretty cool. They're actually sharing technology, and I was pretty excited from that point on. That hey, here's a product that I could take on and add some value and fit my goals as well as my skills, and it was just exciting to me. And again, you always have your questions dealing with the federal government, but actually went very smoothly. Derek was a great help and very responsive, and we just worked our way through it, and it went very smoothly. And then working with Crane has of course been really easy. It's just a great collaborative process, and I don't really have any complaints through it all. So
that's great to hear. Excellent.
Yeah, and from oh, go ahead.
No, go ahead. Sorry.
Yeah, and this is Crane. Yeah, from my perspective, I guess I was excited that the Derek's office picked up on the idea back in 2016 and sort of made this, sort of brought it through into the CRADA process. From our office, we're operational. Our focus is flood forecasting, and it was pretty streamlined to sort of get the CRADA through the system. Let's say, generally agreements are sometimes a challenge in the federal government, and this seemed to flow smoothly. And then it was nice once it was sort of established. I think working with David worked really well. Like I mentioned, we've never actually met in person, but have been able to work closely together and leverage some of the the VLab or the NOAA tools to sort of share in the development of the project. And I think for us, the River Forecast Center, Alaska Region, NWS, it's been a big win to be able to take the sort of leverage Stillwater to make these available back to ourselves, and sort of we can be on to sort of thinking up new ideas and refocus on just our sort of everyday mission of flood forecasting, and have this tool available that we can just go ahead and purchase. I think everybody loves the idea to build them in house, but in the end, I think we're more efficient if we can just procure these and then just get them out there fielded. So I think overall, Derek, it's been no complaints on our side, and was a smooth process. And we definitely, as we have new ideas, would look again at the office to do something similar.
Fantastic. That sounds great. Well, what I'm going to do at this point is shoot it back over to Silver Spring and Katie and see if she has any questions that came through on the webinar.
Thank you, Derek. Yes, we do have a couple questions online. First up, did you have to work with the Alaska Department of Transportation to get permission to deploy on bridges and on road signs? How did that process work?
So yes, we do. We work with the Alaska Department of Transportation and go through sort of our NOAA procedures and their procedures for permitting these installations. And we've done enough in bulk that it's fairly streamlined at this point. We have sort of template application, and we usually get 5 or 10 approved at a time.
Okay, thank you. Next question. What type of wave, chop, surface motion of the river are the iGage and iRadar capable of measuring?
My experience is that it tends to, even when there's not a flat surface on the river, it tends to still make a measurement. I think it's probably up in the air whether you're getting the tops of the chop or the bottoms of the troughs. I think it's, yeah, and so that introduces some error likely when you do have say 3 or 6 inch standing waves along the river. Radar, I'm not sure how the radar is affected by sort of surface roughness, and that would probably be, you could ask the radar sensor manufacturer if they have information on that. But I've noticed it, I think, in the acoustic sensors that it is affected by surface roughness.
Okay,
but you still get a distance return. It's up in the air, I think, or I haven't really nailed down whether it's the top or the bottom of the surface wave.
Okay,
yeah. The way the iGage measures, it takes about 20 measurements, and then sorts them, takes basically the medium measure. So the measurement is over a few seconds. So you may, if it's a moving wave, it would be, again, probably be a mid, but if it's a standing wave, of course, you don't really know. So
yeah, an additional question in that same vein to kind of elaborate. Do you know what the river motion like surface cutoff would be to get meaningful data?
Oh. Yeah, I don't know. I don't know. Have you done anything in that regard, Crane?
We haven't run into any sites where we've had too much motion or too large a standing waves that it wasn't meaningful. We tend to be meaningful for us sometimes is just much we can take lower accuracy if we still get a signal that tells us the river's gone up, say, a foot since yesterday, and it's still going up. But it'd probably be sort of site by site and based on the need. There's places where we have not installed these, and it's because they don't meet the accuracy for the intended use. And so you always have to consider that. But yeah, I think it would probably be sort of site specific and really based on what the need is for the device.
Okay, thank you. We have a couple more questions. Is the data that's collected from these devices, is it public if someone wanted to add it to a regional assessment, for example, like the USGS data?
So all of the gauges that we've deployed and the partners we've worked with to deploy, we then ingest the data into our National Weather Service system, and then those hydrographs I showed, we feed them out through, we call it AHAPS, and it's our sort of public web presence for the Weather Service. And so yes, it's available through the standard National Weather Service public portal. And I guess David could talk about, if a company bought one, I guess whether they make it public or private maybe is up to them. I don't know.
Yeah, this is David. Actually, ours generally are public because we've not really experienced the need for to keep it private. So our web services don't require a specific login or authentication. So in general, they're public, and I don't think there's any private information there anyway. So that's our stance anyway.
Okay. Yeah, so to elaborate on that, someone asked if that data could be sent to MADIS to get into the Weather Services AWIPS systems. That would be something that could happen?
So the way we do it is because we've developed these, we directly ingest through our office from Iridium. But likely, I think with Stillwater offering chef encoded data, it would be fairly straightforward to query that and to ingest into another Weather Service office AWIP system. So we do pull the data into AWIPS, and I don't think it would be too difficult for an office to pull it into AWIPS as well. Whether there's a centralized service or not, either through MADIS or NOAA heads, that may be something in the future that would allow sort of the centralized distribution within NOAA to get it into weather forecast office AWIPS systems.
Okay, thank you. Additionally, Crane, could you elaborate on how you collect and store the data for your system?
So we like I mentioned, we get the data packets directly from Iridium, and it's via, you can either do a socket feed or an email data feed, and we just basically get emails from all these gauges in the field, and then decode those and ingest those into our AWIP system. Similar to what David has to do on his end, it provides maybe a simpler interface where you don't have to sort of spin up and have all the processes in place to decode and ingest and store all the data. But the basic idea is we do the same thing. We go from sort of raw data to people within the Weather Service understand chef data, and then chef data can easily be ingested into our National Weather Service AWIPS, it's called, system for weather and hydro processing.
Okay, awesome, thanks. We have two last questions, and they're both dealing with cost. So would you know what the approximate cost would be to replace, to use the iGage to replace a wire weight gauge?
So I'll let David answer that.
Well, basically, the iGage sells for $1,495 in the onesie category. And essentially, I don't, of course, the cost to replace something else is kind of depends on the installation, but as Crane showed, they can be very easily for a few dollars hung off of a bridge or other structure over the water. So
yeah.
Basically you're talking about $1,495 plus the labor involved. So
yeah, and typically, this is Crane. We've done similar. We have wire weights where we've installed these side by side, and often we don't usually look at them as a replacement, but we augment. Everybody who's worked around automated field equipment knows that they go down occasionally, and so it's always, for us, we like having the wire weight still in place. And that, for people who aren't familiar, wire weight is just a manual. It's a weight on a wire that you lower down by hand to the water surface to measure the river water level. So we often will put these at an existing wire weight site. It's great for calibration, and then leave the wire weight in place. If the sensor were to fail or get damaged, it's still the manual system's still available for somebody to go out and read. But that system takes a person going out into the field. And that's within our office. We had quite a few of those daily wire weight readings, and the idea was to transition to an automated system that would replace the daily, save cost, and provide greater temporal resolution with 24 readings a day instead of 1 per day.
Great, thank you. And I just want to clarify, is the iGage and the iRadar, are they the same cost, or is there a price difference?
No, the radars are significantly, the radar unit itself is quite a bit more expensive. So basically, radar units, depends on which radar you have, will run over $4,000 a unit. So.
Okay, thank you. I believe that's the end of our questions online. If you guys have anything else you would like to add?
No, this is Crane. I think we've covered most everything I've thought about. Thanks for having us again.
Yeah, thanks very much.
Yeah, this is Derek. Thank you guys both for taking the time. We really appreciate putting together the presentation for us. And from our behalf, thank you so much. And for everybody online, keep an eye on the NOAA Library website for upcoming brown bags, but also for our Innovators series. We'll have another one coming up next month and months following that. So we're looking forward to talking to you again.
Thank you, everyone.
Katie? Yeah, I'll let you close it out, Katie.
Yes, thank you. This is recorded. It'll be up on the library's YouTube channel in the next 24 hours. If you missed it or want to share it with colleagues. Thank you, everyone.
All right, thanks.
Thank you.